Ladies and gentlemen, welcome to video number 20 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed in late 2017 at the Bibliothèque Nationale de France in Paris. We are today now December the 2nd in the year 2018, about a year later. Today we start with part 5 of the book The Fivefold Sun, dealing with periodicities in solar behavior that are shorter than the Schwabe cycle. As you see, we are now in millennial oscillations for short, but also including shorter than the Schwabe cycle down to the solar rotation period. The title of part 5, Within and Beyond the Schwabe cycle, from solar rotation to millennial solar oscillations. In part 5, we deal with the contents of today's video, the intra-Schwabe cycle periodicities of less than 11 years, but we'll deal also with longer than Schwabe cycle oscillations, i.e. the multi-decadal and up to multi-millennial solar oscillations. Accepted notions as far as intra-cycle periodicities in the solar cycle are concerned are that these are not really periods in their own right, but quasi-periods. One of the reasons for this restriction is that the oscillations appear to be either ephemeral or intermittent. The most often cited intracycle lengths that are accepted in the field are the 5.5-year period, found for instance in the solar wind, a period of about somewhat less than 1.6 years called the Richer period, seen for example in flares, and 3 periods that are subsumed usually in many publications under a variable periodicity called a quasi-biennal periodicity. These are these 3 lengths, of which the one in the middle, about 2 years, got its name of a quasi-biennal period from the Earth's meteorological oscillation, the QBO. The rationale for the presence of such intracycle periodicities is in the literature that 5.5 year would be a subharmonic of the main cycle of 11 years, half this length, and other periodicities are often invoked as other subharmonics. They would not be related to any specific numbers of rotations of the Sun, but this is not what we shall find today. The issue of periods that are present below the main period of 11 years in solar oscillations has been a concern for more than 1 century. Sampson, the British astronomer royal, a century ago in 1914, in his textbook The Sun, wrote that unlike the study of tides, we don't know in advance what are the component waves which make up this 11-year oscillation, and we are left with the task of bringing up subordinate fluctuations which may be numerous and complicated. For the tides as well, but they come from known entities such as planetary, celestial mechanics oscillations. Schuster actually, shortly before this assertion by Sampson, found many such fluctuations with the tool that he invented, the periodogram. We are still now in 2018 trying to understand these fluctuations. Bretthorst, a statistician, meanwhile, was able to detect 9 sinusoidal components in the relative sunspot number record, which he found to be the 9 largest ones, but he did not trust his own finding, writing that probably, except the 11-year length, all other would be likely artifacts because the oscillations seem not to be harmonic. The solar cycle is not a sine. So in this sense, are there any subharmonics to be found at all? In the Fivefold Sun project, we used from 2002 to 2017 a 15-year effort throughout the same methodology of meta-analysis. And in 2010, a meta-analysis was performed of extant literature to try to find material to assess what these so-called subordinate fluctuations are. We assembled 16 source periodograms or spectra from various authors, and with the task not only to detect the peaks, but also to identify the troughs and compare. And then from the detected peaks between the troughs, to refine each detected period or quasi-period from all extant sources in the literature. The weakness, again as in part 4 for the bounds of the Schwabe length itself, is an arbitrary binning. You see here in this table the peaks that were found and the troughs that were found. The binning here is 2 to 3 years, 3 to 5, 5 to 7 years, and 7 to 9 years. Same binning for the troughs up to 5 years and then larger bins. So the result is in the bottom line where you see what is the mean length for the detected secondary peaks. We have here 2 possibilities for the shortest peak, 2.2 or 2.7 years. We see here that there is a trough in between at 2.5, so we have to refine and go through the literature to find out whether it's 2.2 or 2.7. Then we have 3.4, we have 5.5, and we have 8.4. The troughs will help us refine before we go into the details of the literature and the many parameters and time series that will be useful. If we now translate into numbers of rigid rotations the values that were in the bottom line of the previous page, we find here 30 or 37 rigid rotations, 46 rigid rotations, 75 rigid rotations, and 113 rigid rotations. These are for the secondary peaks, and for the troughs, 34, 44, 86, which, as you can see from the blue arrow, are close to Fibonacci numbers. We found Fibonacci numbers for the fall leg length and the rise leg length of the Schwabe cycle, and for the Schwabe cycle itself, 144 rigid rotations. Now we find another peak at 34, which is also a Fibonacci number, and again a peak at 89. In the trough, we approach here 29, a Lucas number versus 30 for this low end of the estimate of the secondary peak, 47 with 46, it is the next Lucas number, 76, the next Lucas number versus 75, whereas for the last one, 123, the Lucas number is much larger than the found 113 rotations. This is a reminder of what Lucas numbers are from part 1 in the Fivefold Sun as a book. 76, for instance, and it is the sum of Fibonacci number 21 and Fibonacci number 55. In between is 34, which we found is a trough. The largest peak at 113 rotations, it is close to the poloidal cycle of 121 rotations. It is also maybe found at about 120 rotation in neutrino counts time series. But whatever, it is irrelevant because we are too close to the actual Schwabe length of 11 years to have a intra-cycle periodicity that can be combined, compose a full Schwabe cycle. So we will restrict the time domain to lengths that are shorter than 7 years. And we arrive at the longest such intracycle period detected from the periodograms, which is distinct from a whole Schwabe cycle length, the length of about 5.6 years, i.e. 76 rigid rotations and the 9th Lucas number. You see from this table all the several parameters and series that were taken into account in the meta-analysis of the literature to arrive at various subtotals: solar surface, solar interior, solar radius, solar exterior, solar angular velocity if available. And we find an average of the subtotal parameters of 5.59 years, or maybe a little bit higher than 5.61, very close to 560, which is the theoretical value of 76 rigid rotations. For the presumed set of quasi-biennal periodicities, we find three distinct fluctuations. One is actually, as already well known in the field, a 3.4 or 3.46 year quasi-period, which is extremely close to 47 rigid rotations, the 8th Lucas number. Same for the 2.14 year well-known QBO solar and also terrestrial period, 29 rigid rotations, 7th Lucas number. And for the third in this set of so-called quasi-biennal, 132 year, it is 18 rotations with a very small error bar. We have authors who proposed, for instance, these authors proposed that multiplying by 8 we find the Schwabe cycle length for the previous period, the previous page. Apostolov proposed that multiplied by 5 you get the solar cycle length. But such authors contemplate the possibility of a harmonic. We will see that it is not a harmonic, it is something else. There are also some shorter intracycle fluctuations that approach Lucas numbers. For these we have weak evidence of only 1 or 2 or 3 or 4 reports in the literature. But for the 145 reports that square with such Lucas lengths, from these we can compose this general statistic in which we see here the QBO with 29 rotations, etc. And using the rigid rotation of the Sun as a base value, we see that the other intracycle lengths of more than one rigid rotation, up to 7 years or so, they are multiples of the rigid rotation of the Sun, which are equal to the mean and extreme ratio, 1.618, at a certain power times this rigid rotation. For instance, for the quasi-biennal oscillation, the exponent is 7. This is merely the definition of a Lucas number. Now we can reconstruct how a Schwabe cycle is composed of a set of an integral number of Lucas frequencies. What is found is that the integral number is itself a Fibonacci number. For instance, for the 29 rigid rotation length of, this is the QBO, which is 5 times multiplied by 5 is approaching the Schwabe cycle length, you find the product is 145 rigid rotation, which approaches one by excess of just one rotation, the actual value of 144 rotations. And here in this shaded area, we have all the products of Fibonacci numbers by Lucas numbers, which have as a product 144 plus or minus only 3 rotations. So you see those that are in the bottom or in the top have too much variance to be effectively composing a Schwabe cycle, and we do not detect them in observations. Also, those that are multiplicable by only 1 or 0 can hardly compose any Schwabe cycle and must be excluded. So we see a theoretical definition which squares very well with the observed detected periods. Finally, we close this video with 2 questions. First, do the intra-Schwabe periodicities cause the decadal cycle? We can contemplate this possibility in the spirit of Samson and before him Herschel, who thought that the tides were composed of a certain number of components, and they could find the components in the solar oscillations that compose the main cycle. We will leave the answer to this question to other researchers who are encouraged to look into the matter. The second question, what is the cause of these Lucas periods? We have 2 possibilities at hand. One is that they are underpinned by longitudinal circumstances, maybe longitudinal symmetry operations. We have hints of this from data in the torsional oscillations and in the behavior of active longitudes. Second possibility is that it is merely a result of a hemispheric lag between north and south, each having a certain sequence of Fibonacci numbers of rotations, which are, as is well known, lagged. This might perhaps suffice to explain the Lucas numbers, because Lucas numbers are sums of Fibonacci numbers. This is the end of video 20. In the next video, we will go into the longer than Schwabe cycle oscillations. I thank you for your attention.